we now want to do an example with the Carnot cycle and see how to calculate some of the quantities that we talked about in the last couple of videos. The temperatures at the hot and cold reservoirs, the amount of work drawn from the hot and cold reservoirs, the amount of work done, and then the overall efficiency of the engine. So consider a Carnot cycle that looks like this. And initially at point A, our gas is at a pressure of 8 atmospheres and a volume of 1 liter. And then we have an isothermal expansion, and we go to 4 atmospheres and 2 liters. And then we go through adiabatic expansion to point C at 2.05 atmospheres and 3.242 liters. And then isothermal compression to 4.1 atmospheres and 1.612 liters, and then adiabatic compression. Okay, so how can I find my temperature of my hot and my cold reservoirs? Well, we're going to turn to the good old ideal gas law. Now, these are all in atmospheres and liters, and typically this would be in pascals, cubic meters, moles, and then the ideal gas, or the gas constant, is going to be in units of moles, cubic meters, and pascals, and Kelvin. But instead of converting all of these into their SI units, we're going to convert R into the units of atmospheres and liters. And by the way, our gas contains 0.2 moles, okay? And it turns out that if you convert R, its typical value of about 8.13 into atmospheres and liters, it turns into 0.082. So R is very closely 0.082 in the new units of atmospheres and liters. We're going to, of course, leave this in moles, and we'll leave this in Kelvin. But we can now calculate what T hot is, because remember that this is isothermal, so between A and B, this is going to be the same temperature. So at points A and at points B, this is going to have the same temperature, and this is when the engine is in contact with the hot reservoir. So we can calculate our hot temperature as PV over NR. Okay, and if I multiply 0.2 by 0.082, then I get 0.0164, and this denominator is going to have the units of atmospheres times liters per Kelvin. Okay, it's going to have the units of atmospheres times liters per Kelvin. So that way my atmospheres and my liters cancel out, and I'm just left with 1 over Kelvin, which is the same thing as Kelvin. And if you do that calculation, that's very close to 488K. All right, so this is 488K. And we can do the same thing for T cold, except we can use these numbers. And if I run the math here, again, this is going to be .0164, and if I do my math here, I'm going to get about 403 Kelvin. So now I have my temperatures. Now we need to worry about the hot and cold amounts of energy, QH and QC, right? So remember, we can get those from our specific heat equation. And if I plug in my values here, and my pressure at VB, or my volume at VB is 2 liters, and my volume at VA is 1 liter, so this is going to be the log of 2. And I'm being sloppy with my units here, but part of the reason is this is not going to come out in joules, so we'll just call it energy units, okay? Because we have converted R away from our standard SIs, the number here is not going to be joules. So if I do my math here, I'm going to get roughly 5.55. And EU here stands for energy units, okay? Now, why am I not really too worried about what the energy is? Because the ultimate goal of any heat engine is to get the efficiency, okay? I can get the efficiency. So that's what we're really after. We really want to know what the efficiency of this engine is. If you really, really want to, you can convert this number into joules via whatever the conversion factor of R is, and convert your atmospheres into pascals and your liters into cubic meters. But for our purposes, we're not so concerned about that, okay? So for right now, EU just stands for energy units. So now the Q cold this should be Q hot. Whoops. So now Q cold. Yeah. Instead of VB over VA, we're going to take VD over VC, but again, we get the minus sign, so this is going to be VC over VD. VC, so this is going to be 3.242 divided by 1.612, and this is the log. Okay, so now if I run these through my calculator, I get right around 4.58, right? And again, that's 4.58 energy units, whatever these units of energy are, right? So now we can calculate the work. And this is going to be roughly, what, 0.97 or so. Right? So I'm doing work of 0.97 energy units for every unit of energy that I bring in. Now, as you can see, this is not likely going to be a very efficient engine. Unfortunately, this is the efficiency of a realistic engine, okay? This is the efficiency of a fairly realistic engine. The hot and cold reservoirs on the Kelvin scale are really not that far apart. They're less than 100 degrees. And in truth, a lot of engines that we encounter in mechanics and engineering and so on and so forth, machinery, are roughly of those types of temperatures. And so what we're essentially saying is that real engines are not efficient at all compared to the ideal case of 100%. There is no such engine, again, as in fact the Carnot cycle is as good as we can really get in truth, but compared to an ideal engine, if it existed, our engines that we have are simply not that efficient. Your car is anywhere between 10 and 20% efficient. So what is the efficiency here? And so my efficiency is going to be 1 minus 4.58 divided by 5.55, and this is roughly 17%, or 0.17. I can also compare that to the efficiency calculated with the temperatures and make sure that those efficiencies agree. And indeed, if you punch that in your calculator, you will see that this is indeed 0.17. The trailing decimals don't necessarily agree, and that's due to rounding error between our two numbers, but to the within the rounding that we've done, these answers agree. And so that is how you can find the efficiency of the Carnot engine. If you wanted to find the work in joules, you would actually want to convert these out of atmospheres and liters, but for our purposes, it was much easier just to convert the gas constant and do one conversion instead of 8 different conversions. All right. So I hope that that didn't throw you off too much, but the process, once you get whatever units you're going to work with, once you get those confirmed, then the process is exactly the same, and that is how you do it. Hope this was helpful to you, and we will see you next time.